Hello class. We will now discuss how we can turn a list of outcomes in a probability experiment into numeric values. A random variable is a variable whose numeric value is determined by the outcomes of a probability experiment. Let's look at an example. Suppose we flipped 3 coins and we want to count the number of coins that turn up heads. To do so, we will first look at the sample space, and we can use a tree diagram to find all of the outcomes. So remember that flipping 3 coins is equivalent to a first toss, a second toss, and a third toss, so we can create our tree diagram with heads and tails, and from each of these outcomes, we can continue our list of outcomes, and traveling down each branch, we get our 8 possible outcomes. Heads, 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 tails, heads, tails, heads, heads, tails, tails, and so forth. From this, we can see that the number of coins that turn up heads can be any number between 0 and 3. Notice that this outcome has 3 possible heads, whereas these 2 outcomes have 2 possible heads. This outcome has 1 possible head, 2 possible heads, 1 possible head, 1 possible head, and finally, no possible heads. So we can have no heads, 1 head, 2 head, or all 3 heads. This is because some outcomes show no heads, some show 1, some show 2, and one of them shows 3. So let's summarize. A discrete random variable counts the number of possibilities for a specific event. The notation that we will use, we let x represent a given random variable. In our last example, x was the number of coins that turn up heads. X is a discrete random variable. Remember from chapter 1, discrete data count, right? So this random variable is going to count. We can now use this idea to calculate probabilities for each numeric possibility of a random variable. For example, the probability of getting 3 heads is the probability that our count is 3, and it's 1 over 8, since there is only 1 outcome of the total 8 possible outcomes where all 3 coins show heads. Remember that x counts the number of coins that turn up heads. So in this case, we want to portray a count of 3. So again, we write our count, our random variable, which counts, equals 3. Putting this all together, we are now able to define a discrete random variable, list all possible outcome numeric counts, and calculate a probability for each. We can portray this in a table we call a discrete probability distribution. So a discrete probability distribution is a table that gives the probabilities for every value of the random variable x such that the following properties are true. All probabilities are between 0 and 1. The sum, remember this sigma represents our sum, the sum of all of our probabilities equals 1. So knowing that, let's now create a discrete probability distribution for our previous discrete random variable. So we're letting x be the number of coins that turn up heads after flipping 3 coins. Okay, so the table will contain 2 columns. The first column will be titled x and will list each individual possible value for our discrete random variable x, capital X. In our case, we know capital X is allowed to be 0, 1, 2, or 3. So we create the first column with these values. So we have all of our possible outcomes. We can get 0 heads, 1 head, 2 heads, or all 3 heads. The second column will be titled P of capital X equals X, and this will list each respective calculated probability. So remember, going back to our sample space, one of the 8 possible outcomes had 0 heads. That was our tails, tails, tails. And then 3 of our 8 possibilities had 1 head. 3 of our 8 possibilities had 2 heads, and 1 of our 8 possibilities had all 3 heads. So these were calculated, again, using techniques from 4.1 along with our sample space. Notice that this probability distribution satisfies the 2 conditions, since all probabilities are between 0 and 1, right? The 1/8 was 0.125, and 3/8 is 0.375. All of those are between 0 and 1. And if we sum all of the probabilities, we get 1. 1/8 plus 3/8 plus 3/8 plus 1/8 is actually 8/8, which simplifies to 1. Now you try. So a fun problem, create a probability distribution for X, where X is the sum of 2 rolled dice. Okay, so think about that one. So again, this goes back to chapter 4 where we rolled 2 dice. So we had that large sample space consisting of 36 possible outcomes, but now we want to look at the sums of those dice. So let's pause the video and try it yourself, but here's the solution. Remember from chapter 4, we had our 36 possible outcomes. This can be seen using a tree diagram. We can now look at the sum of each pair. So if we sum 1 and 1, we get 2, 2 and 1, we get 3, so forth. So we notice that each sum, the lowest we can be is 2, and the largest we can be is 12, and we can get every value in between. So our first column, and I'm going to write it as a row since it's a larger setup, I'm going to turn the columns into rows, which is fine. So my X is allowed to be 2, 3, 4, all the way up to 12. And again, I'm using this idea here. Now I need to find the probabilities of each. So remember that the probability of an event is the number of outcomes that satisfy that event over the total number of outcomes. So if we look at P of X equals 2, this is our sum equals 2. So the sum of the 2 dice equals 2. That's what this statement is telling us. Our event is the sum of our roll is 2. There's only one outcome that satisfies that, and that's the outcome 1 and 1. So I roll a 1 and I roll another 1. So my probability is 1 over 36. However, if we wanted to calculate P of X equals 5, this is the sum of the roll equals 5, we would count all outcomes where the sum is 5. So notice that 4, 1, 3, 2, 2, 3, and 1, 4 all satisfy this event of equaling 5. So we get 4 out of 36. So listing all of these outcomes, we get the following probability distribution. Now again, I did not simplify these. Your homework and your quizzes and your exams will ask these to be simplified, whether they're simplified fractions or decimals. But I've left them here so that you can easily verify that this is what you get when you do it yourself. All right, we will now discuss how we can find the mean, standard deviation, and variance of a discrete probability distribution. First, let's discuss notation. When we create a discrete probability distribution, all possible outcomes for the given probability experiment are known. That is, we know the population. We are able to list all outcomes. So we will use the notation mu, sigma, and sigma squared to denote the mean, standard deviation, and variance, respectively. Remember that these are our population parameters. Going back to chapter 3, we saw that we use our lowercase Greek letters to represent our population parameters. The mean, or expected value, for a discrete probability distribution of a random variable x is given by mu equals the sum of xi times p of xi. This is sometimes denoted by e of x. So sometimes we call it the mean, mu. Sometimes we think of it as the expected value, and we use this notation e of x for expected value of x. Now, this tells us to take all of our values, our possible outcomes in our probability distribution, and multiply them by their respective probabilities. Then we take the sum of these products. The standard deviation for a discrete probability distribution of a random variable x is given by the following. Note that the variance is the square of the standard deviation. So again, the variance just squares this value, so it's just going to eliminate this square root symbol. Even though these formulas are given to us on our exam formula sheets, again, we will utilize our calculator, the 1var stats feature, to make our lives easier. So let's look at an example. Find the mean, standard deviation, and variance of the given discrete probability distribution. So here we have our possible outcomes. So we can get a 14, a 21.5, or a -2. And here we have our respective probabilities. So the probability of getting a 14 is 0.3. The probability of getting 21.5 is 0.4. And the probability of getting -2 is 0.3. So what we want to do is we want to open our calculator and again click our stat feature. This is what we used in chapter 3. We're going to highlight our edit and click edit. Again, this is how we edit our lists. In L1, we're going to put our x values. So we have 14, 21.5, and -2. Now we're going to think of this a little bit like a grouped frequency distribution, and we're going to put our probabilities in our column L2, 0.3, 0.4, and 0.3. And we're going to go back to our home screen. So we're going to click second and mode so that we exit out and return to our home screen. We're going to once again click our stat button and highlight our calc feature. This is where we calculate statistics, and I'm going to click my 1var stats. Now I'm going to tell my 1var stats to pull up my data from L1. So again, I click second and number 1 for L1, and then I'm going to put a column and say, hey, think of this like a group frequency distribution. So pull my kind of frequencies, or in this case, probabilities, second 2 from my column L2, and I'm going to close off my command function here. And then I hit enter, and notice that my mean, this is my expected value, or my mu. So my mean is 12.2, and notice that they don't give us an SX because they're confused at why there's decimals, but they do give us a sigma. Remember that our standard deviation is represented by sigma. So this is our standard deviation, approximately 9.80102. Okay, so this is exactly what we saw from our screen. Now again, if we want to calculate our variance is just our standard deviation squared. So I'm going to take my standard deviation, 9.801020, and I'm going to square it, and I get approximately 96.059993. Now, again, the book has a rounding rule here. I always like to be safe and use 6 decimals when I'm using a decimal number in a calculation. So it's your preference whether you want to follow the book's technique or follow my technique. This is the safer route and will always get you the correct answer.